Before this, you learned how to take given thermochemical equations and manipulate them such that you could calculate the standard enthalpy of reaction for a given chemical equation. Well, now you need to learn how to write your own equations and then how to get the data yourself. There is a format to the chemical equations. So let's learn how to do that. We'll work through this one and then do a few more after that, do some pattern matching. Look at the product. It's 1 mole of product and it's just one product. As far as the solid, you're not expected to know the physical state of lithium fluoride. That will be provided to you. Looking at the reactants, they're written in a special way. What elements are in lithium fluoride? Lithium and fluorine. Now, fluorine is written as F2 because when you isolate the element fluorine, it exists as a diatomic. So you need to go back and review which elements are expected to be found as a diatomic. For the physical states, this is something else you need to go back and review. What we call the elemental or natural state of the elements under 1 atmosphere or 1 bar of pressure and room temperature. So lithium is expected to be found and isolated then as a solid. And when you isolate fluorine, not only is it a diatomic, but it's expected to be a gas. So go back, review those physical states. The coefficient in front of the F2 is a 1/2, and that's because 1/2 times F2 gives me 1 fluorine. That's for the product, lithium fluoride. Previously, when balancing a chemical equation, if I had just given you the lithium plus F2 makes LiF, lithium fluoride, you probably would have done this to avoid fractional coefficients. You can't avoid fractional coefficients anymore. So the bottom one is not written properly because it's for 2 lithium fluorides and it has to be written for 1. I know I haven't explained why yet. The standard enthalpy of reaction is defined to be the difference between the enthalpies of the products and the enthalpies of the reactants. Then for this equation, because of the way it's written, we can give it a slightly different label. So look on the upper right. I put a subscript F because now this is a standard enthalpy of formation. It's for the formation of solid lithium fluoride from its elements. And if you look that value up, it's not in the tables I provide my students, but you'll see that it is exothermic and it's 616.9 kilojoules for every mole of solid lithium fluoride formed from its elements. And the negative is on there because it's exothermic. Now I'm going to show you a diagram. If you want, feel free to blow right through it because I just want to give you an idea where we can get this information. This is an example of a Born-Haber diagram. We start with solid lithium and diatomic fluorine gas. Well, the goal is to make lithium fluoride solid, so we have a number of processes that we can think about that will allow us to get there. One of them would be to vaporize the lithium, solid to gas. That takes enthalpy. It's an endothermic process. Then we need to remove an electron from lithium to make it the lithium ion. That's also endothermic. Then we break the bond between the fluorines and diatomic fluorine. So then we have atomic fluorine. That's endothermic. That electron that we removed from lithium gets transferred to fluorine. That's an exothermic process. We have lithium gas and fluoride gas. So if we put these together to make solid lithium fluoride, that's an exothermic process. This is a cycle from beginning to end. So the enthalpy difference between the initial and the final is an enthalpy of reaction, and since we wrote the reactants and the product in a special way, it becomes an enthalpy of formation. A couple things about this equation. So we already did this. It's a difference between the enthalpies of the products and the enthalpies of the reactants. Well, we make another definition, and that is the standard enthalpy of formation for any element is defined to be 0 kilojoules per mole. Be careful on that element. If you look up the value for O2, gas, it's 0 because it's defined to be 0. In fact, in the table of data I give my students, I don't even include it because you're expected to know that it's 0. But if you keep looking, you'll see these two values there also. For monatomic oxygen gas, O gas, it's positive 249.2 kilojoules per mole. And for ozone, O3 gas, it's positive 142.7 kilojoules per mole. So that natural state, the most stable state, is important. By defining the standard enthalpy of formation for an element to be 0 kilojoules per mole, we don't really mean it doesn't have any enthalpy in it. So to give you an analogy, in lab, when you weigh something out on the balance, a common practice is to put a piece of paper or a plastic weighing tray on the balance, and then you push the tare button. Now the balance reads 0, and it's not because the paper or the weighing tray has 0 grams, it's because you've offset it. So that's what we do. We make a definition that our elements for the standard enthalpy of formation are assigned a 0. So then if you look back on the top, the difference between lithium fluoride solid and its elements is negative 616.9 kilojoules per mole. And then by defining our elements to be a 0, we then get to take that negative 616.9 kilojoules per mole and stick it on solid lithium fluoride. And now we can use that value whenever we need it. Even if the chemical reaction cannot proceed the way it's written, the enthalpy difference is still valid. Let's write a few. Solid sodium chloride. And why solid? Because I picked it. What's in sodium chloride? Sodium and chlorine. What physical states go on those two elements? Solid and gas. And then, for balancing, we put a 1/2 on the diatomic chlorine. If you look up the value, negative 411.1 kilojoules per mole. It's an exothermic process, and for every mole of sodium chloride produced from its elements, negative 411.1 kilojoules. Dinitrogen tetroxide. What elements are in that? Nitrogen and oxygen, N2 and O2. Both of those are gas, and we put a 2 in front of the O2 to make it balance, and then you look up the value for N2O4, positive 9.1 kilojoules per mole. It's an endothermic process. Solid calcium sulfate. Don't think of that as calcium sulfate. I know we did that before, but you need to now think of it as a compound that has calcium, sulfur, and oxygen in it. There's calcium, sulfur, and oxygen, the elements. Calcium and sulfur are solids. Oxygen's a gas. Oh, reminder on sulfur. Sulfur is more appropriately described as S8. However, most books, and I'm going to follow along with that procedure, write it as just S. So that way you only have to worry about the diatomics. You don't have to worry about sulfur and phosphorus. Those would just be S solid and P solid. And then you put a 2 in front of the O2 to make sure it balances. And then you look up the standard enthalpy of formation for solid calcium sulfate. Negative 1434.5 kilojoules per mole. Acetylene gas, C2H2. What elements are in that? Carbon and hydrogen. Hydrogen is a diatomic. Solid for carbon. Gas for hydrogen. Put a 2 in front of the carbon. And then look up the value, positive 226.7 kilojoules per mole. Previously, I did a problem about calculating the enthalpy of reaction for that bottom one, but we used 3 thermochemical equations. They involved the combustion of acetylene, of carbon, and of hydrogen gases. And we got positive 226.6. Well, 0.6, 0.7, just a rounding issue for the data. And all these data, including the data on the table I provide students, you may notice something curious in that all the data appears to be magically rounded to 1 decimal place. That was a personal choice on my part. They're not always 1 decimal place, but I did that on purpose. I will comment on looking up states. As I mentioned earlier, you're not expected to know what the state is supposed to be for a product. It will be whatever it's given. But the states are important when you write this out. Here I have 2 of them, hydrogen gas, oxygen gas making water, and I didn't put a state on either of the waters, but notice on the right-hand side, I have 2 different standard enthalpies of formation. Let me go put the right state labels on these. For the top one, it's gaseous water, and for the bottom one, it's liquid water. So the states are critical. Don't forget them. The reason for the difference between the liquid and the gas, it takes enthalpy to vaporize something. So that's why the value for the gas is smaller than the value for the liquid.